Hello, everyone. It is day 1 of Unit 9, and we are going to talk a little bit about bonding. That's the whole focus of this unit. Just a reminder, if you haven't already done so, please go back and watch the Zoom meeting from today. That will kind of give you some background, where we've been, where we're going, just to sort of put some context into these notes. So go ahead and do that first. All right. The first thing I want you to do actually is just a quick organization thing. I'd like you to update your table of contents. It just keeps your notebook a little bit more organized, not for right now, but for weeks or months or years from now if you need to look back at it. So April 13 through 16 was our Unit 8 periodic trends, really short unit, but packed with lots of great information about why the periodic table looks the way it does and what information we get from it. Okay, but now we're ready to move on to Unit 9. And the objective for today is to connect electronegativity values to the types of bond that can form between elements. So your EQ then is maybe something like, well, how do I use electronegativity elements? Or how do electronegativity values determine the type of bond? Something like that. So go ahead and set that up at the top of your notes so then you have that focus of what's the whole point of these notes. So at the end, you can write your summary. You can use it as review later, but just so you kind of have an idea of what the whole point of this is. Let's get into it. So the whole point of today is thinking about where does that bond come from? So how do we become a bond? So why do atoms connect with other atoms? Why don't they just stay separate? Why does that happen? Well, the most simple answer is it's to be stable. But now we can be a little bit more specific about what that means. It means that they're filling their S and their P sublevels, which gives them those 8 electrons that we've often talked about before, because S2 and P6, that equals 8. So that's a huge deal now. Instead of just making up that number where 8 came from, that's why that is more stable. And then so that's why they do it. So then the other focus is, well, how does an atom connect with another atom? And it's all about electronegativity. And that's, of course, related to lots of other things like size and nucleus and shielding and all that stuff. But electronegativity is what we're going to focus on. So just a reminder, electronegativity is how likely can an element pull an electron or attract an electron from another atom to itself. So visually here, so here's 2 different atoms. So this nucleus is holding on to its own electrons, but then also maybe trying to attract an electron from another place. So that's what this is showing. And then same here. This atom has an attraction between its nucleus and its own electrons, but then also trying to maybe pull that electron. Electronegativity is how likely will this atom be able to attract this electron to itself, or how likely is this atom to attract that electron to itself. That's electronegativity, and that's what guides all of our understanding about bonding. So the nucleus is pulling on electrons, and then that can cause an attraction. It can cause a connection. And then there's 2 general types of bonds or connections that we talk about. You maybe remember these from before. Ionic is when one nucleus pulls so much, it can actually take the electron from the other atom. That creates an ionic bond. And then the other option is that both of the nuclei are pulling on each other's electrons, and neither one is really much stronger, so they end up just sharing. Those are the 2 general ways we would describe bonding in kind of this new context of nucleus and electronegativity and pulling, that kind of idea. An ionic bond then, just again to define this, is when 2 elements have been lost, or when 2 elements are gaining or losing electrons, and then at the end, they create what we refer to as a formula unit. So this idea, here's an atom, here's another atom. This nucleus must have been stronger because it pulled the electron to itself, creating a transfer of electrons. So now this has an extra electron, which makes it negative. This has one less electron than normal, making it positive. This ending thing would be called your formula unit. And the attraction between them, or the connection between them, is referred to as an ionic bond. The other option, just a little bit more detail then, is the covalent bond. And that occurs when 2 elements, between 2 elements, when the electrons are being shared. So here's a visual of that. So this nucleus is attracting its own electrons. This nucleus is also attracting these electrons. So this would be your shared pair of electrons. And that connection, because this nucleus is pulling on these electrons, this nucleus is pulling on this electron, this is now referred to as a molecule. They're not separate atoms anymore because they are connected by that attraction from the nucleus. And that's referred to as a covalent bond. However, between these 2 types of atoms, there could be a difference in nucleus. In this visual, it looks like they're about the same, but they could be different. So there's really 2 types of sharing. You get a polar covalent bond when one atom nucleus is noticeably stronger. So it can attract or pull the electrons a little closer, and it creates partial charges. So not full ions, but these little symbols. It's kind of like a fancy D with a hook on the top, or like a fancy S with that closes, however you want to draw it. But it's the Greek letter delta, and it means it's a partial charge. So for example, these are electronegativity values, and you can see that hydrogen's is smaller than chlorine's. So when they create a bond, chlorine, it's not strong enough to take hydrogen's electron, but it pulls the electrons a little bit closer. Think tug of war. So chlorine is a little bit negative because the electron that's being shared is a little bit closer, but it hasn't won tug of war, because then that would be ionic. Hydrogen, then its electronegativity value, meaning its nucleus is a little bit weaker. So then the electron isn't taken from it, but it's a little farther away. So it creates that partial positive. So these are your indication that you have a polar bond. It's not being shared evenly. Nonpolar would be, well, both nuclei are about similar in strength. It doesn't mean they're both weak. It means that they're both similar. So then these are when the electrons would be shared equally. So like this is an obvious example because they're the same atom. So of course they're going to have the same kind of nucleus. And so when they play tug of war, neither team is either winning at all. They're both just pulling on those electrons, attracting them as much as they can, but it doesn't go anywhere. So they just kind of stay in between evenly in this molecule. So those are kinds of some things, some more details related to ionic and covalent bond. But the big question is, well, how do we determine which one it is? And it's by looking at the difference. So literally just subtraction, difference between two elements' electronegativity values, and then that will tell if it's lost, gained, or shared. If it's a small difference between the two values, most likely they're going to have to share it because one isn't strong enough to take it. But if it's a larger difference, that's when one nucleus can actually take an electron. And that would be gaining, and meaning the other atom would have to be losing because its nucleus is not strong enough to keep attracting its own electrons. And that's all based on electronegativity differences. So what we're going to think about is nonpolar bond versus polar covalent bond versus ionic bond. And really, polar can be weak or strong. We'll get into that in just a little bit. And so you can actually look up electronegativity values. And then again, this idea that when you look up the two values, if one of them is noticeably higher than the other, that means that it's going to be able to take an electron. And if it's not much higher, then it's going to have to share. If you take out your fancy periodic table, if you don't have yours anymore, there is one on Schoology, so you probably want to download that into Notability or print it if you have an option. It's called the Fancy Periodic Table on Schoology. But if you remember the one I'm talking about, you're going to take that out and you're actually going to turn it over to the back side. And on the back side, it actually has all the electronegativity values listed. And at the top bar on the back side of the Fancy Periodic Table, it has the electronegativity differences. And then that's going to tell you what percent of ionic character does it have. So like 100% ionic character means it's super ionic, gaining and losing electrons. And then, if it's like 60%, that's still pretty ionic versus 2%, that's not ionic at all. So then that probably would be like nonpolar. And then there's kind of a breakdown. Now these are general ranges, but generally if it is a small difference in percentage, that means it's not very much of a percent ion, so it's nonpolar. A little bit more we call weak polar bond, a little bit more strong polar bond. So meaning that, again, the difference between here is that they're sharing unevenly because one nucleus is stronger, but it's not so strong that it can actually become an ionic bond and take the electron. So this is when you'd have those partial charges, no charges at all, and here you'd have full pluses and minuses, full ions. Let's go ahead and practice this to see if this makes a little sense. So you've got the fancy periodic table, but then remember it's on the back side. And on the back, on the top, you'll see this, the percent ionic character. In black, it lists the difference between the electronegativities. Literally, you just subtract. And then that corresponds to what percent of an ionic character is it. So the higher percent it is, the more likely it is to be ionic. The lower percent, the more likely it is to be nonpolar. So if you look at this, again, this is on the back of that fancy periodic table, you'll see these squares that look like this. The number in the upper right is your electronegativity value. So already we can see, look at hydrogen compared to beryllium. Hydrogen is more likely to attract electrons to itself than beryllium is because this number is higher. It doesn't mean these two things will be able to bond. I'm just comparing the values. And then on the other side of the periodic table, so same thing, right? So these are just like oxygen and fluorine. So what I would do then is I would say, oh, well, let's compare hydrogen to oxygen. So if I subtract these two numbers, 3.44 minus 2.20, I get 1.24. That's the difference in electronegativity. So 1.24, so that kind of is between these two. So it'd be maybe like around 32%. So that means that in terms of it being an ionic bond, it's about 32% of that, meaning it's not all the way ionic. It's more likely to be a polar bond. So that's the idea. But I just wanted to show you what you're looking at to be able to determine this. So the back of the fancy periodic table, find this thing. You're looking at these numbers up here. Let's do some examples really specifically. So here's all of that stuff that I already showed you, the range of the different types of bond. And let's do NO2. So nitrogen is trying to bond with oxygen. It would do that 2 times. Nitrogen with one oxygen and nitrogen with another oxygen, creating a molecule. So first you're going to look up the values. So this is on the back of the periodic table, the upper right, you would find these numbers and you would just copy them down. So now I've got these two numbers, but then we need to find the difference between them so that we can compare it and find the percent ionic character. So the difference between them is 0.40. You literally are just subtracting its absolute value. So what is the difference between those two numbers? 0.4. So then I look at this thing. This is on the back of your fancy periodic table. A 0.4 difference equals a 4% ionic character. So how much is it likely to be ionic? Only 4%. So super low. Then we go up here, a 4% difference means that this is going to be a nonpolar bond. So when nitrogen and oxygen bond, neither nucleus is strong enough to actually pull electrons at all. They just kind of hover between them. It causes a connection because the two nuclei are attracting those electrons, and it creates a bond. It creates a molecule, but not strong enough to have any partial charges or full charges. That's the idea. Let's do one more example together. Same thing. Here's the range. Let's do boron chloride. So boron and then chlorine. So this would happen 3 times, boron and chlorine, and then that would happen 3 times to create a molecule or a compound. I look up the two values. So boron is 2.04, chlorine is 3.16. Again, this is coming right from the periodic table. You just copy it down, subtract it, you get 1.12. So literally you're just subtracting them, absolute value, just the difference between those two values. You look at this chart, 1.12, so it falls kind of right between there, so kind of right between here for percent ionic character. So I maybe would say 27%. If you said 26 or 28, it's not going to matter that much because they fall in the same range. So then this we would call a strong polar bond. So when B and Cl compare to each other, the chlorine, because of the higher value, is the stronger nucleus. So when these two play tug of war, chlorine pulls the electrons a little closer to itself, which means then this would be partially negative. Boron would be partially positive because this nucleus is a little bit weaker. So the electrons are pulled away from it a little bit, creating that partial charge. And why do those partial charge thing matter? It's for something we're going to learn more later. Like, well, what does it mean if there's partial charges? What does that mean about melting point or solubility or any of those other properties related to bonds? So that's kind of the idea of looking at electronegativity values to figure out bonds. Go ahead and pause the video and do a level 1 question so far, something really basic right from the notes, just to kind of think about what you've learned so far. All right, come on back. I actually have another objective for you. Now we're going to use what we've kind of learned or what we know about ionic compounds to draw something called a Lewis dot diagram. And you can just continue on the same page if there's still room, or go to a second page, but I'm just going to consider this one set of notes, like for cost equations and summary, but you can split it up if you want to. But it is a separate objective. So your second goal for today is to be able to draw Lewis dot diagrams for ionic compounds. Let's get into this part. First, I want to talk about, well, why do we care about ions and why are they more stable? Well, this we can answer by looking at valence electrons. Remember that valence electrons are electrons in the outermost energy level. We care about them because since they're on the outside, they're the ones that take part in bonding. And that's what we're learning about this unit. Really, you can also think of it as electrons in the highest S and P sublevels. And remember, that's where we get that 8 from. So for example, if I had strontium, and if you were to write out or look at your periodic table or your Aufbau diagram to get the the electron configuration for strontium, this is what it would look like. So then what we do is we find the outermost energy level, the highest level. Well, in this case, 1, 2, 3, 4, 5 is the highest level. We count any S's or P's that are in the highest level. Where in this case, there is no P, it's just 5S. So then that means this is our valence electrons. There's only 2 of them. And then that would tell us some things about strontium in terms of gaining and losing electrons, oxidation numbers, stability, and that's the thing that makes this kind of cool. Here's another one, germanium. Again, if you were to write out the electron configuration for germanium, you would get this. And then if I want to figure out the valence electrons, I need to find the highest energy level, the highest S and P. So 1, 2, 3, 4, 4, back to 3 and 4. So I've got 2 places where there's the highest level. So it is not just the highest sub-level. So it's not just the end, 4P2. There's also a 4S2. So 4 valence electrons, 2 and 2. So be careful with that. It's not the highest sub-level. It's the highest energy level, which was 4. It's not 3D because 3 is not the highest level, 4 is. So those are some of the things that are easy to just make mistakes on. So just be careful about this. All right, and let's just do one more to make sense. Sulfur. So again, if you were to write out the electron configuration for sulfur, this is what it looks like. We're looking at the highest level or the S and the P. So I go 1, 2, 3S and a 3P. So I add these up, 6 valence electrons. And again, this is going to tell us something about how stable is sulfur. Is sulfur more likely to be to gain electrons or lose electrons? And also this would tell us about light and those kinds of things too, but we've kind of moved on to talk about bonding now. So that's one way to find valence electrons, writing out the electron configuration. But the other thing you can do is just look at the blocks on the periodic table. So like, look, sulfur is here. If you go back to the beginning of the row and count the S, 1, 2, and the P, 3, 4, 5, 6, or 4, 1, 2, 3, 4 plus 2, you get 6 valence electrons. Well, that's what we figured out on the other one. So if I did something like indium, D block is never going to be your highest level because remember the S's always fill before the D block does in the same row. So if I'm at indium, I go back to the beginning and I count the S, 1, 2, and the P block, 1. So there'd be a total of 1, 2, 3 valence electrons. It'd be the same thing if you were doing something here like tantalum. So you count the highest energy level, which would be S and P. So if I go back from tantalum, here's the only highest level we have is S, so 1, 2. So tantalum would have 2 valence electrons. So that's the idea of how you find valence electrons. Count the S and the P block, or you can write out the full electron configuration, but you don't have to. So let's draw this. This is a visual way to represent valence electrons. And they're called Lewis dot diagrams because they're named after Gilbert Lewis, who wanted a visual for representing how stable are atoms or ions. So it shows the valence electrons because then that's going to help us see how stable they are, knowing that 8 is the goal. So it's time for some examples. Let's do a couple examples. You can either put these on your notes or flip over to your output page. A couple examples for Lewis dot diagrams. Let's do the sodium atom. If you write out the electron configuration for sodium, it's this. Or if you look at where sodium is on the periodic table, it's in the first column, which means it just has 1 in the S. So if you're counting S and P, this would be 1 valence electron. So literally you do the symbol and a dot. This dot represents the 1 valence electron. So that's going to tell us that sodium is not stable. It does not have 8 valence electrons. In fact, it probably wants to lose this electron because look, if this electron goes away, the lower level will have 8 electrons, and then that would be stable. Well, let's think about that. That's what sodium does to become stable. It creates an ion where it loses an electron. We've learned about that in Chem 8. It's going to go backwards on the periodic table to be like neon, getting rid of that outer level. And then this is what the electron configuration would be. 1s2, 2s2, 2p6. Here's your 8 valence electrons. So then I would have my 8 dots, but just be careful because you might be like, well, wait a second. How come sodium can look like this and it can also look like this? We need a special notation. Think about it. What did sodium have to do to get from this to this? Think about it. Yeah, it had to lose an electron. So anytime you have an ion, you also need to put brackets around it and its charge. +1 because it got rid of a negative electron, so it has a plus charge now. So then that shows us, oh, this is not normal sodium with 8 dots. It's only like that because it lost an electron. So ions will always have brackets and charge. Let's try another one, the fluorine atom. Well, here's the electron configuration, or you could look at the periodic table, find where fluorine is. It's in the column next to the noble gases. So if you go back to count the S and the P in that row, you'd have 2 from the S and 5 from the P, or like we have here, S2P5, that's 7 valence electrons. So you drew the symbol and then 7 dots around it. And you can see that we seem to always put the dots in pairs if they can. That is a format for Lewis dot diagrams, not just a Killinan thing, but that's how they're drawn. And then that tells us that, oh, fluorine is not very stable, or it's not stable yet, but hey, if it gained 1 more electron, it would be stable. Let's do that. So then the fluorine ion would say, hey, I want to fill up this 2p sublevel because then that would make me stable, and that's what it does. So then if I give it its 8 dots, like this shows 2s2, 2p6, there's my 8 dots, but again, this is not what fluorine looks like normally. Normally it looks like 7. So remember, what do we have to do for ions always? What was it? You got it, brackets and charge. So I put the brackets around the fluorine with the 8 dots, and then it gained an electron. And electrons are negative, so gaining an electron will make it stable. So -1 charge. And then you can maybe start to think where we're going with this. What would happen if these two things got near each other? A negative and a positive? We'll come back to that later. All right, go ahead and do a level 2 question. You could pick a different element, any element on the periodic table, and ask for its Lewis dot diagram. That would be a great level 2 question. All right, welcome back. We got one more little section. You notice that all of the ions always had 8 valence electrons. Again, that's where we get that octet rule. Every atom wants to have 8 valence electrons. That full S and P make it stable. And then this is why we've always referred to that one special group on the periodic table that already has 8 valence electrons. They already have a full S and P. Which group is it? You got it, it's the noble gases. So every noble gas, if you write out their electron configuration, it will end in S2P6, S2P6, S2P6. Don't let this confuse you. This is a lower energy level, so it doesn't count. Same with this one. And here we throw in an F, doesn't matter, right? Because it's the S and the P that are always the highest energy levels. All right, so that just kind of gives you, again, trying to connect things we've learned before and why this is the right answer. 2 quick little reminders before we finish off today. Just a reminder about ions. There's 2 versions of them. Cation is one of them. And remember, it was my little joke that, oh yeah, cations lose electrons because remember, cats have pos, right? So they're positive because they lost something negative. And generally, if you look at this on the periodic table, these are the metals. Well, let's think about why this is. All the elements on this side, think about what their highest level is. It's anything that's in the S. So then they're going to be more likely to want to get rid of these levels because it's like an S2 probably, because if they get rid of that, their next level down likely will be full. So because they're on this side of the periodic table, it's just their S's that are filled. So then if they get rid of that S sublevel, they'll be like the noble gases. So this is why metals are more likely to be positive. Anions were the other version of an ion, and these have gained electrons. And my silly little thing is like, oh, it's negative to have ants at your party, right? So an anion, like ants, so that's negative. But the point is that they gain electrons. It's the opposite of a cation. And then again, this is generally the non-metals. So if you look at where they're on the periodic table, look at this. If they're on this side of the periodic table, they're likely to have their S's filled and part of their P. So it's going to be less energy to fill the P level, sublevel, and be like the noble gases instead of getting rid of all of the P, all of the S, and going backwards. So again, trying to make connections of why do elements do what they do, with some more context of electronegativity and nucleus and their valence electrons and electron configuration. All of that comes together to help us understand bonding a little bit more. So then now that we remind ourselves about cations and anions, the last piece of this is now to put compounds together. You might remember from the earlier part of this video that an ionic compound forms because one of the nuclei is more affected. It has a higher electronegativity value, so that it can actually pull. It pulls an electron to itself, meaning that one atom is losing the electron and the other atom is gaining it from the one that lost it. So the one that is more effective is gaining the electron from the one atom that has the weaker nucleus. So here's a visual. Sodium and chlorine, between the two of them, chlorine has a stronger nucleus. It has about the same number of levels, right? 1, 2, 3, 1, 2, 3 levels, but the chlorine atom has way more protons in its nucleus, so the nucleus is more effective. Same shielding, but chlorine is more effective. So chlorine pulls the electron from sodium because sodium is not pulling that electron as tightly, and then that pulls away. So then you can see here was their original Lewis dot diagrams. Here's their original electron configurations. The 3s1 now fills up the P5. So then now you've got 1s2, 2s2, 2p6, there's 8 electrons. And then you've got 3s2, 3p6, there's 8 electrons. The only thing is that, remember, these should have brackets around them. These should have brackets around them. And then that's now positive because it lost an electron. This is negative. And then now these two things would connect to form a formula unit. But what I want us to practice is the Lewis dot diagram piece of it. So how do we draw a Lewis dot diagram if we have an ionic compound? Well, let's go back to that example with sodium and fluorine like we did earlier. We said that the sodium, if this is an ionic compound, for sure it's going to be the sodium ion, always 8 dots, brackets, and a +1 charge. Fluorine, because it's an ionic compound, it'll be the fluorine ion, so automatically 8 dots, brackets, and charge. Well, look at this. They're a perfect match. They're going to attract to each other. Remember when I asked you that earlier, what you thought was going to happen? Positives, negatives attract. This is now a stable compound called sodium fluoride. So instead of it just being sodium and fluorine, it's NaF. That would be the formula. Sodium fluoride, that would be the name. Let's try another one, aluminum and chlorine. So again, aluminum is always going to be an ion because we're making an ionic compound. Sorry, because it's making an ionic compound, aluminum will always be an ion. Because it's making an ionic compound, chlorine will always be an ion. So we don't have to figure out how many aluminum valence electrons it started with. Instead, we automatically give it its 8 dots. So aluminum with 8 dots, but we need the brackets and the charge. So here's where we have to look at where it is on the periodic table. It's in the P1 column. So if it loses the P and both S's, that is easier than filling up the rest of the P sublevel. So then that's why it's a +3 charge. Chlorine is one of the halogens, so 8 dots. It's 1 column away from the noble gases, so it's going to gain 1 electron, -1. So they both have 8 valence electrons now, but look at this, a +3 and a -1. Chlorine wants to take 1 electron from aluminum, and it can, but aluminum's not stable yet because it has to be able to give up 3. So then another chlorine is going to join this compound. So this chlorine takes 1 electron from aluminum, but again, that's not stable yet because it has to give up 3. So another chlorine joins this compound. So this chlorine takes 1 electron. This chlorine takes 1 electron. This chlorine takes 1 electron. Now, this whole thing is a stable compound. So when you draw these, be picky about where you draw them. You can't put the chlorine here because the chlorine is not taking from another chlorine. It's taking from the aluminum. Also, you can't put negative charges next to each other. They would push away and they wouldn't make a compound. So it does matter that you put negatives and positives next to each other, or you put what is gaining and losing next to where they're gaining and losing. So that's important. So that's how you would draw a Lewis dot diagram with ionic compounds. And then now this would start to help us understand some things about shape and properties and solubility and other things, which we'll talk about later in this unit. Go ahead and finish off these notes with a level 3 question, and then go back to your 2 EQs. Answer those EQs as your summary to kind of cap off all this new information about why atoms bond, how they bond, and then also some introduction on ionic stuff. And that's the end of our information for today. If you didn't do so already, make a Unit 9 Notability folder and put the Unit 9 plan from Schoology into Notability so you have that organization. There's 5 or 6 days in this Unit 9, so you can kind of see what we're doing each day. You have the list of objectives. It tells you which unit practice problems you could do today so that you have that information. If you didn't already do so, go back and finish your Costa questions from today and your summary. And then today, I just like you to do some of the unit practice problems. I don't have a new assignment for you. It was a lot of information today. So for sure, you want to do something to process it, whether it's going back and doing your Costa questions, maybe you want to do a few extra Costa questions, go back and do your summary, or doing a few of the unit practice problems is going to be a good way to see if this made sense. And then that's it for today. We're going to see you at our next Zoom meeting. Have a great day. Thanks for joining in. We'll see you next time.